Okay, we're going to look at an example of collection of a gas over water. And this experimental technique can be used to get information about a gas produced in a chemical reaction, or through stoichiometry, the reaction itself. So in our example problem, we have a reaction, and in that reaction, potassium chlorate is decomposed to produce potassium chloride and oxygen gas. And in this setup, the oxygen gas produced is going to go through this tube here and up and into this area. We have a dish filled with water and a bottle partially filled with water that is inverted into the dish. And so there is a place up here at the top where the oxygen can be collected. And we can also, by geometry, know that volume, and we can measure the temperature. So those known volumes and temperatures are given here in the problem that we're looking at 19 degrees C and 735 torr. You can read that up at the top. And so when this reaction is carried out, it produces gas into completion. The height of the bottle can be adjusted so that the atmospheric pressure outside in the surrounding environment is equal to the total pressure here. So the total pressure up here is going to be equal to the atmospheric pressure, and that total pressure is given at 735 torr. Okay, so when this reaction takes place, the total pressure that's going to be maintained up there is going to be equal to that of two gases. The two gases are going to be the oxygen produced by the reaction and the water that is up there due to the fact that water has a certain vapor pressure at that temperature. And so the total pressure of the gas is going to be equal, by Dalton's laws of partial pressure, to the pressure of the oxygen produced by the reaction plus the pressure of the water, which is the vapor pressure of water. And the total pressure is going to be known, and the vapor pressure of water is known as a function of temperature, so that will allow us to calculate the partial pressure of oxygen. The total pressure minus the vapor pressure of the water will equal the partial pressure of my oxygen. That is going to be 735 minus 16.5, which will then equal what, 718.5 torr. Okay, so that is going to be the pressure of the oxygen. Now, using the ideal gas law, PV equals nRT, and if we use the pressure that is the pressure of oxygen, that will be produced by the number of moles of oxygen. So now, since we know the volume and the temperature, that will allow us to figure out the number of moles of oxygen. P of oxygen, V over RT will equal our number of moles of oxygen. The pressure, you notice we have to use the partial pressure of oxygen, so that will be 718.5 torr. but I want to use my R value that includes atmospheres, so I will need to convert that to atmospheres. That will give me a pressure in atmospheres. My volume is given as 327 milliliters. That is 0.327 liters. My gas constant is 0.0821 liter atmospheres per mole Kelvin. And my temperature is given at 19 degrees C, and I can add 273 to get my temperature in Kelvin. My units will now cancel. I have my temperatures in Kelvin. My torrs cancel, giving me a pressure in atmosphere. My atmospheres cancel. And my liters cancel, giving me my N in moles. And doing all of that math, I get 0.0129 moles of oxygen gas. Now, my original question asked how many grams of potassium chlorate were consumed. And so I can go back to my original reaction. I'll rewrite that here. And now, through stoichiometry, I know that I have 0.0129 moles of oxygen. In the stoichiometry of my reaction, I can see that I have 2 moles of potassium chlorate for every 3 moles of O2. I can then convert that to grams. The molar mass of potassium chlorate is 122.6 grams per mole. And that will give me 1.05 grams of potassium chlorate. So that tells me that there were 1.05 grams of potassium chlorate consumed.